Hi! This video is part of a series in which I learn about programming a retro video game on the Commodore 64 in assembly. The code I'm using is from the game Supernatural, written by Georg Rottensteiner. You may also know the game as Guns and Ghosts. This is not a tutorial, just me learning game programming. Enjoy the video. Coders, good morning. Morning to me, and not even that. It's in the middle of the afternoon. Today is going to be a short one, but we're going to save the high score table to disk. And I say specifically disk because the code was written with that in mind. Yeah, well, it's a choice. Doing it on tape is a little bit more difficult because the thing is that we're going to be writing a high score table, a piece of memory, to a device, and we're going to overwrite the previous one. So the thing is going to have a file name, and it is going to be overwritten on the next iteration. So doing that on tape is difficult because tape doesn't have a directory to, you can't find a file name in that sense. You can do a single load and that's it. I'm not going to show the game running. You'll just have to. There's not really something to show. I could show a file name on disk, but I'm just going to go through the code. If you've ever looked at handling files on disk on the Commodore, then you know it's a bit archaic. You work with logical file numbers, so each number is given a handle. This is not strange in programming at all. It's also given a device number. Now, the device number could be a screen, or it could be a printer, it could be a tape, or it could be a drive. And then there's the secondary address. Now, the secondary address's function depends on the device, so it behaves differently for tape devices than it does for disk devices. But we'll see a couple of things, and just we'll just go through it. Let's get started. So the trick is to save the high score data, so the high score and the high score names to disk. And what is going to happen is that the bytes starting from this location down to this location will just be written to disk. And when we open the file, we read the information again and write it to memory and save it from in this same space. So this bit of memory is going to be manipulated by our disk routines. So there's a high score data end that wasn't there before, but we need to be able to calculate the end address because we're going to indicate a start and an end address. Then a little bit higher up, we are going to handle names. Let's start with this. There's a drive number. It is set at 8, so that 8 means the first disk drive device. Disk drives have device numbers starting from 8 and up. There's a high score file name, which is just called high score. You can't change it. It's just called that. It also has a length. It's 9 long. 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah. And there is another copy of that thing, but then with this in front of it. Now, again, Commodore's BASIC, its original BASIC was, it had a load and a save and a verify, and that was about it. It didn't have a delete function. So in order to delete a file off disk, you had to open a channel for that device and send a command. Now, this is a disk command. This is the scratch command. S0 means scratch for device 0. I'm not going to go into why that is another device number. That's all ancient history. But this is how it works. And then the file name, and we need an address for where the delete file name ends. So what you have to know is that if I send this as a command to the drive, it's going to delete this file name. So what we will see is that when we save the high score table, we delete the old one and then write the new one. If we didn't delete the old one first, the kernel would come back with an error message saying, "Oh, file exists." You can't overwrite files by default. So, and that opens the door to the next thing that because we're gonna scroll back up now. All the way at the top of the code now, and you can see that there are some kernel routines. We had some kernel routines already. Then they were deleted. Now they were added again, and now they're in there twice because you can see them. They're here as well. Note that these addresses, FFD5, FFBD, and all those, they point to a vector table. A vector table is basically a list of addresses that point to kernel routines. That would allow Commodore to make changes to their code quite easily, so that people could, a previous code could still call this, but the vector would point somewhere else. They could just put in a new address in there, and then your code would do the same. So that sort of forward compatibility thing, but not really necessary to know that. But these are our routines. I will go into what they do as we go through the code, but note that they're in there double. It's no biggie, but it's just the way it is. Now, when we start our code, I'm scrolling down now to the first bit. This. Also note that some of the addresses here, they don't have a label yet, but BA hexadecimal is the 0-page address that holds the last device number used. We're calling it drive number here, but it's not fair because it's a device number. So, what we do is we load whatever's there and we store that to the variable drive number. I don't think we've seen that yet. I may have skipped that actually. Let me see what that. I'm just gonna go to the declaration of that. All right. Oh, okay. It was the drive. Oh, okay. That's this. That was. We didn't skip it. We saw it actually. Now back to where we were. 163, I believe. Right. So we've initialized it with 8, but what we're doing is we're initializing it again with 8. That's basically what we're doing. No, that's not true. We're loading a number. We're setting that to drive number. If it was not 0, then we don't need the default drive number. But if it was 0, i.e. we haven't used any device yet, then we just put in 8. But 8 was already in there, so unless someone used drive 9 to load the game, then this will be 9, and it won't be overwritten by 8. So this is just a service to our friendly gamer. And then we do load scores, so we get right to the meat of the thing. The loading is easy. The first thing that we want to do is suppress kernel messages. Things like any message that the kernel can give, like error messages or loading or what when you type load at the basic prompt, the messages that follow are kernel messages. Now, when you're in game, you don't want those messages to appear, so you can suppress them. And writing 0 to this. To the accumulator, and then calling this routine means that you suppress all messages. There are some alternatives, just suppress basic messages or just suppress some I just read the manual on them, but I didn't remember all of the combinations. But 0 means no messages at all. So then we start setting up our loading. So we use logical file number 15, which is arbitrary in my mind, but 15 is one of those easy to remember numbers. Everybody uses channel 15. Then we X holds our drive number, and Y is the secondary address. Now, when you are handling disk drives, the secondary address 0 and 1, they have the same meaning as when you load a file off disk, 8, 1. If it's 0, it'll load the information to the address that you set, which we'll see in a minute, because that's what we're doing there. If we write a 1 here, the kernel routine will look at the header of the information coming from disk and write the information there. So if the programmer definitely wants the data to go in a certain location, he will include that information in the header, and you load the program with a 1, and it'll load to that location. But we just want to set it by hand, so we make the secondary address 0. Now this secondary address functions differently for tape drives and printers and whatnot, so I'm not going into that, just the thing that we need here. Now we need to set the file name. We have to set that because we'll get an error if we don't. We set the name length, which was 9. We set the X and the Y registers to the highscore file name, which we just set, which was just the highscore name. And then we call this routine. So we've done the logical file stuff. We've set the name. Now we have to set up the actual load. So we choose 0 for load. We set the X and Y register to where we want the stuff to load, highscore, and we call load. And that's when the magic happens. If this works without an error, then the data will just be in memory. The way to check whether it worked or not is to check the carry. If the carry is set after loading, then there is a load error. Notice, by the way, the German comment here. Okay. Anyway, if there is a load error, then we return 1. If there was no load error, we return 0. No load error, we return 1. So if there's a load error, return 0. No load error, return 1. And that's it. So either it works or it doesn't work, and the load routine doesn't do anything to repair it. Just didn't work. If it doesn't work, then it's just going to be the old highscore table that we programmed in there. So it's going to be the default table. Then, of course, there is a moment at which, and I'm going to have to look that up. 737. There we go. This here, notice, by the way, this text thing is still in there. It hasn't changed. It's unused. It's just a bit of memory that's sitting there. Anyway, at the end of the highscore table changing, just before we jump to the title screen, we call save scores. This is the only call that we do at the end of that thing. So when we've changed something in the table, we do save scores, right? Easy. And what is save scores? We haven't seen it yet, but here it is. It's comes right after load. First of all, we're going to have to delete the old file name. So we take the highscore delete file name end and subtract the highscore delete file name. So this was the highscore file name with the S0 and the colon, and we actually calculate the difference. The This means that if we edit this file and give the file a different name, then this is going to function. In the load version, we had a fixed 9, so but this is how code develops, it's not final and it's not perfect, but this works, right? X and Y we set to the address of the delete file name, and then we call the set name routine. So this is part 1. Then we set logical file number 15. We set the drive number. We set the secondary address to 15. Now, we've just talked about the secondary address. If it's 0 or if it's 1, those are different functions. Then 2 to 14 are something else, and 15 is a command. So if we typed 15, 8, 15, it means that we're going to send a command. So we set the logical file stuff, and we're telling the kernel that we're going to send a command, and then we call the open routine. So this doesn't just open the file, it opens the file but with the scratch command in front of it. So this is going to attempt to remove the file. If it comes back with an error, then for some reason or other the file couldn't be opened. Probably it didn't exist yet. So in that case, we'll do error delete. If the file was there, it's been deleted now, and then something odd happens because we take the logical file number 15 and we call checkout. Now, it's not really clear what this does to me, because that file number was already open. We had the drive number, we had the secondary address. Would you just take the file number, we close it, and then we set the file number back to 0, back to normal. This bit of code, I'm not entirely sure of. Maybe it's because the open with the command changes the file number or whatever. Anyway, after we've deleted the file, we have to sort of close the channel and then reset everything, and then we can jump to save now. So we have to put everything back to normal. So this must be, I don't know, I'm going to have to look further into this, but I couldn't find anything logical about this. Why we have to change the file number to 15 when it's already there, and then must be something in there. I may come back to that. Anyway, in the error situation, what happens? We just write an A character to the screen. Now this is all rock hard, This is just a fixed address and a fixed number, and we just write just to indicate to ourselves that something happened, and we just put something on the screen and then we close. So if we couldn't delete the file, the story ends. If we could delete the file, then we can just save what we already had. Now this is where the normal stuff happens again. So we take the length of the file name, the start and the end. We set the name stuff. We set the logical file stuff. So in this case, we use channel 0, 15, and secondary address 0. We get the address of the highscore. We were saving, but now we're all of a sudden we're using, these are the addresses actually that are used to store that information. So all of a sudden we're doing this by hand. So we're setting the address of the highscore information, then in C1 and C2. That's the start information, and then the end information goes in X and Y. So this is a pointer to the start. We write that there, and a pointer to the end. Because, we're saving data, so we have to indicate what is saved and how much. And then we set the start address located in C1, C2. So we have to indicate where that is, and then we call save. I'm going to have a cheeky peek at the save routine here. FFD8. I'm going to make you, you probably can't see this. Save is used transfer directly from RAM to IO device. Since the save routine performs open, must be preceded by setlfs. Setnam. The file on the save is performed without giving a file name. See, tapes don't even have file names. A page 0 pointer to the starting address of the area to be saved should be set up with the low byte of the address first. The accumulator should be loaded with the page 0 offset of that pointer. Okay, so that's just how save works. And these addresses, because I looked them up, and they normally hold that information anyway. So this is apparently how it works. And then we call save, and the thing does if the carry set, a save error happened, but we're not doing anything with that. Sorry, we couldn't save your table. Nope, just end of story. So I don't know how long I've been going on. A couple of minutes. That's it. There's no other changes in this episode. So I hope you enjoyed it. I hope you learned something, and I'll see you in the next one. Don't be square. See ya.